Hello, today we're going to be talking about salt, more specifically sodium chloride, with an exception of ammonium chloride. And we're going to be discussing the chemical properties of salt and how it influences our daily lives. We're going to be starting with chemical reactions involving salt, and then move on to solubility and morality of salt, followed by salt's role in water's freezing point depression, and ending with salt's role in rusting and redox reactions. And to start us off, we have Vanessa.
There are many chemical reactions involving salt. Salt can usually be found in natural forms, such as the salt in the ocean water, but it can also be a chemical reaction. According to reagent, salts are often the product of neutralization reactions between acids and bases. For example, table salt, also known as sodium chloride, can be made through the neutralization reaction of a hydrochloric acid and sodium hydroxide, forming table salt and water. Another way that salt can be produced is through combination reactions, such as the reaction between metallic sodium and gaseous chlorine, as shown on the screen. While both sodium and chloride are highly reactive with water, when they are combined, table salt has its good uses in everyday life. Some of these uses include flavor enhancement, which suppresses bad flavors and reverses bitterness due to the vitamins and minerals in some foods like vegetables. Salt is also used for preservation. By reducing water activity and soaking up the water through osmosis, the salt creates a sort of dry environment where there is little room for bacteria, causing rot to grow. A real-life connection involving salt would be the process of making bread. Salt is used to improve the flavor of bread and balances the yeast fermentation process. A big role that salt plays in making bread is that it slows down the yeast fermentation activity through osmosis, preventing the yeast from growing too quickly and making the dough too airy and weak. According to Cargill, although salt is good for making bread, too much salt could cause the yeast to be dehydrated and eventually kill due to the process of osmosis. Now that we have gone through some chemical reactions and examples involving salt, I'd like to reiterate that salt can also be found in natural forms such as fresh water and salt water. Now, Jack will talk about the solubility and molarity of salt water.
An essential topic we learned in Chem 110 is molarity and solubility. Molarity can be defined as 1 mole of solute divided by 1 liter of solution. A common example of molarity that we will explore is the molarity of fresh water versus seawater. Salt, or in this scenario, NaCl, is very commonly found in seawater, where in fresh water it is not commonly found at all. According to Jack Powell on sciencing.com, freshwater may contain small amounts of salt, but not enough to be considered saltwater. Ocean water has an average salinity of 3.5%. This means that there are 35 grams of salt dissolved in every liter of seawater. Solubility directly relates to molarity. Solubility can be defined as the amount of solute that can be dissolved in a certain amount of solvent at a specific temperature. Increasing the temperature of a solvent directly increases solubility or increases the amount of solute you can fit into your specific amount of solvent. Another important factor of solubility is saturation. When a solution has reached saturation, it can no longer absorb any more solute into the solvent. An example of this would be if you were to put 2 tablespoons of salt into a glass of water, and the water only has the ability to absorb 1 tablespoon. The other tablespoon is left to sit at the bottom of the glass of water and does not get absorbed. Now, Isaac will explain how different salt concentrations can be helpful or harmful.
In Chem 110, we explore states of matter and freezing points, which are important for understanding how salt helps melt ice. Water freezes at 32 degrees Fahrenheit under normal conditions, but when salt, or in this case sodium chloride, is added, it separates into sodium and chloride ions. According to How Stuff Works and Britannica, these ions disrupt the hydrogen bonds between water molecules, preventing them from forming the organized molecular structure which is required for ice. By interfering with these molecular interactions, salt lowers the freezing point of water, allowing it to remain in a liquid state even at a sub-freezing temperature. According to How Stuff Works, a 10% salt solution can lower water's freezing point to about 20 degrees Fahrenheit. The more salt added, the greater the disruption to the water molecules, further depressing the freezing point. However, as the temperature drops below 15 degrees Fahrenheit, sodium chloride becomes less effective because there isn't enough liquid water present to dissolve the salt and release the ions. Understanding how salt works is important as it has many real-life applications. According to Britannica, salt is often spread before snowstorms to prevent ice formation and improve traction, making winter driving safer. Pedestrians rely on salt to reduce slip hazards on sidewalks and driveways. This science directly impacts public safety by reducing accidents caused by icy conditions. However, SafePaw emphasizes environmental concerns related to an excessive use of salt. It can lead to damaging plants, soil, aquatic ecosystems by altering the water chemistry. Alternatives like calcium chloride or less environmentally harmful solutions are often used in these cases. Another inconvenience of an excess of salt is that it can also contribute to the rusting of cars left on roads treated with salt, which Bella will now go further into.
A quick recap of what we've learned in Chem 110 with redox and half reactions pertaining to rusting. So we can see that in rusting, iron loses 2 electrons, and in oxide, it gains 4 electrons, which reduces to 4 hydroxides. And so real life applications from the article provided by Dr. Lair in Chem 110: to prevent rusting, we can keep cars and bikes dry, which could be parked indoors or in the garage. We can wash them regularly and try to avoid the beach. And now we're going to go beyond voltaic cell. So the picture provided is a voltaic cell, or a salt bridge that you're familiar with in Chem 110. And so from our previous knowledge from Dr. Lair's class, we know that salt bridges allow flow to neutralize the charges, and it separates the anode and cathodes. And so we're going to look at other voltaic cell usage. We're going to look at dry cell batteries, which is a typical battery you can find at Target or that you use, and we'll see that as a AA battery. So according to an article on Dragonfly Energy, they say that for a dry cell battery, they do not use salt bridges. It serves as the same function, but they call that an electrolyte paste. And they call it a dry battery because there's no liquid electrolyte used. And for the salt in a dry battery, according to Fahad's YouTube video, ammonium chloride has a positive terminal, and the ammonia moves towards the cathode, and then the negative terminal of chloride moves towards the anode, and these two neutralizes the charges. And zinc chloride, it maintains acidity and electrolyte and improves the battery performance. And so again, salt bridge and the voltaic cell that we're used to seeing, including the dry battery that I just talked about, both have redox reactions, which means they both have half reactions. So in the dry battery half reaction, we see that zinc is oxidized, and which means it's losing 2 electrons, and then oxide is gaining 4 electrons, which reduces to 4 hydroxides. Where is the salt present in a dry battery? So the salt is the ammonium chloride. This is what's acting as a salt bridge. It's just not called a salt bridge. The salt bridge in a dry battery is substituted for the electrolyte paste. The salt bridge and the electrolyte paste, they are both serving the same function. They are both separating the anode and cathodes, and they are neutralizing the charges, which have the main goal of preventing a short circuit. We have our references.
Thank you.